Is it visible?
Yes,
Just
sir.
hit the record button, please. Record buttons. Okay. Okay, guys. So previously, guys, thank you. We were in moment area method, and we discussed how to use moment area method for working out deflections in cantilever beams. Yes. So the cantilever beam problem we did. We were in the middle of finding out deflections in simply supported beams. Yeah. So I'll just try to recap what we did in the case of simply supported beam and quickly just run you through a very simple example. Okay. So in moment area method, we have got, as we know, two magic formulas. Okay, one is the area, which is equal to 1 by n plus 1 b times h. Okay, that is the area formula, and what's the other one? The x bar, which is 1 by n plus 2 into h or b. Okay, so if we can have different cases. Let us test it. I mean, whether it's B or H, let us test it. Okay, let us use our common sense to see whether it's B or H. Okay, because there is a tendency to just forget it. So let us test our common sense. Okay, the main thing is that we develop a common sense. So, okay. So these are the different areas which we can have in our structure analysis. So in this case, n is equal to 0. In this case, n is equal to 1, n is equal to 2, and n is equal to 3. All of them have got weight B, and this one okay, this one is 8. So the area is 1 by n plus 1 b times 8. So n is depending on the degree of the curve. And your x bar, which is what? Which is the distance. So x bar is actually the distance is the distance of centroid of the area from the maximum magnitude, maximum ordinate of the area. Okay, so that is your x bar. So x bar should be H or B. It should be B, obviously. So this is not correct. This is B because this is the centroid. It gives you the centroid of this area, and so x bar is B. So just try to use your common sense if you get confused, like whether you should write B or A. And always you can always test it on your rectangular cross section. Okay, you know that rectangular cross section is half BH, and you know that the centroid from the maximum ordinate is x bar is what? X. Yeah. So B over 3. Okay, that's our centroid. So this is what we developed. Okay, this is what we have done. Now we make use of these areas to find out actually the area of bending moment diagram or M or EI diagram. So these are used, these areas help us finding out the area of bending moment diagram. Okay, now in the case of bending moment diagrams, if you draw it for all the supplied loads, okay, normally we have got one bending moment diagram, isn't it? And that involves the contribution of all different types of load which are subjected, which are applied on the structure. So you can have UDLs, you can have UBLs, you can have uniformly distributed, varying, and concentrated loads. Okay, so any combination of these loads can be applied. But the problem is that when you draw an actual bending moment diagram, you get combination of different curves. Okay, so therefore we feel the need for bending moment diagrams by parts. Okay, we draw the bending moment diagram by parts, which means that for each and every load we draw a separate bending moment diagram. Okay, so you take one strategic point inside your structure, okay, and draw the bending moment diagrams for all the applied loads, okay, considering that strategic point as fixed. Okay, so that's a fixed point. In other words, like, you can have a free point and a fixed point. In a cantilever, you have a fixed end and you have got a free end. So in the case of any sort of structure, any sort of determinate structure which is given to you, you take one strategic point and you find out the bending moments caused by all the applied load corresponding to that point. We call that point as fixed point. In other words, you assume that you have got a fixed support at that point. Okay, you will have set of moment diagrams because you draw it for different loads. Yes. Then after that, so why are we going through this exercise of, in other words, decomposing your bending moment diagram into different parts? Why? Because we want our bending moment diagram to be in certain to involve these areas. And since we know the area and the centroidal distance for all these areas, so then it's easy for us to find out the area of the whole bending moment diagram. Okay, area and the centroid. So that's the main idea behind it. Now, in the case of simply supported beam, what happens is that, imagine I have a simply supported beam which is subject to some load. Okay, so let us take some dimensions to it. Okay, I've shared the chapter which I'm using for this lecture. Okay, I've shared that with you. Okay, so please remember that in exam I will give you questions either from the examples, okay, or from the exercise, but those problems which have got answers. If you go through it in the exercise, you have got problems, lots of problems, but some problems have got answers and some problems haven't got answers. Okay, so I think so the alternate problems have got answers. So only do those problems which have got answers. Okay, and I'll give you out of those. and similarly look closely into the examples. Okay, so that you guys have to do. Now there can be different scenarios. Okay, we have got this simply supported beam which is subject to some loading, and we are asked in the question to find out deflection at a particular point. Okay, so we are asked to find out deflection at a particular point. So what is the first step? The first step is just do the structure analysis. Structure analysis meaning that you find out the reaction. So what is the reaction? So this is 300 into 2 divided by 3, which is 100 meter, and this has to be 200 meter. Now, if we are asked to find out deflection at 1 meter from the left support, okay, so how can we do that? How can we find out the deflection from the left support? Now the elastic curve would be something like this. Yes? Imagine this is V. We are asked to find out delta B. Okay? Now, yes. No, we are reaching. I am telling you that in this case, you can have a scenario where you are asked to find maximum, so that we will do. First of all, I am saying that if you are asked to find out the deflection at a particular point, okay? So, in case of deflection at a particular point, how would you find that using moment area method? That's the first thing we are going to do. Then I'll let you know how to find out the maximum deflection and all that. So, now, what we can do is we can draw a tangent over here. This is our elastic curve. Okay, let me not draw it in dash as a dash line. Let me make it solid. Okay. So, what is this? This is tangential deviation of C when tangent is drawn at A. That is our TC by A. Okay? What is this? What is this?
B by A.
This is tangential deviation of B when tangent is drawn at A. Agreed? Now, what we are interested in is delta B. Okay? So, what we can do is, first of all, we can find out our tangential deviation of C when tangent is drawn at A. Yes? Then using the similarity of triangles, we can find out this thing, this magnitude, which is, imagine BB prime. Okay? We can find out BB prime using similarity of triangles, can we? Yes? And once we do that, then we can find out the tangential deviation of B when tangent is drawn at A. We can do that, and once that is known, then we can subtract it from the BB prime and we find out our delta B. Does that make sense?
Yes.
Okay, so that's how. So let us try. Any question about this? Any question? Yes.
Similar triangles, with two similar triangles.
So what I'm saying is that we have this is TC by A, agreed? And this is BB prime. So this triangle, this whole thing, and these one. These are two similar triangles, aren't they? Is that understandable? Yes. Okay. So now the point is, where should we have, where is the reference point corresponding to which we draw our bending moments? Which is the best point where we can draw? So your aim should be, first of all, that point should give you these areas, okay? And you should get the least number of areas just to make your life easier and have less calculations. Yes? Is that okay? So which point would be best to take my reference point or a fixed point? If I take, imagine this is A, B, C, and if I take D as fixed point, okay, if I take D as fixed point, then I would have C and 100, this one. Yes, that's what I would have, won't I? If I have C as fixed point, then I would have 300 and 100. So I mean, it doesn't matter whichever point I take. Okay, I will always end up with two moments, two moment diagrams. Okay, or moment areas. So, so let us take fixed point at C. So 100 into 3 is 300. Yes. So should it come above or below? Below, according to our sign convention, that is positive. Okay. So this is our 300. And then we have 300 making 300 times 1. Sorry, this is plus. So this is the 300 caused by 300 Newton load, and that one is the load caused by the reaction at A. Please notice that at C, what do we expect? What is the moment? 0, isn't it? And we are getting 0 moment. Okay, so that's a sort of a check for you. So this is a moment diagram by parts. Is that okay? Now, as I said, first of all, we will find out our tangential deviation of C when phasor is drawn at A, which is equal to area is it okay? Yes? Sorry? Yes, so this would be So area AC is equal to into 3 by 3, which is 1. How much is this? How much is this? 400. That is our TC by A. Okay? Now, we'll try to find out TB by A. Or let us find out DB prime. Make sense? BB prime. This is straight line. Similarity, perpendicular by base is equal to perpendicular by base. TB by A, which is equal to
Sir, you have written that result. Sir, BB bar is equals to TC by over 3 by
perpendicular by base is equal to perpendicular by base. What is this area? 300 by 3 is equal to this by 1. So, so this is 100. Agreed? So this is half into 100. Is this okay? Now, what is our delta B? Minus and BB prime is
divided by
And what does that work out to?
706.
So what is 700 by 6? Can you do that? Huh?
116.
116 to 6.
So that is your delta P. Is this okay? Any question? Any question? I'm going to rub it off. Sorry? BB dash. How did we get BB dash? Okay. What is BB dash? Okay. Shall I rub it off? Yes, yes, yes.
Sir, what is x, b and db by 1 by 3?
TB by A is this one. So XB is 1 by 3, isn't it?
Sir, please,
It's a
can you show it, sir? Exactly which,
look.
from which point to which point?
This is your maximum magnitude. XB bar is 1 by n plus 2. So n is 1. 1 by 3 into what?
Okay, sir.
Sorry? What is this? This is 1, isn't it?
Okay,
So
sir. all
1
right.
by. Is it okay? Yes? I'm gonna rub it off, okay? Any question, please ask me. Okay. So that's how we can find deflection at one point. Now, if we are asked to find out maximum deflection, yeah, how can we work that out? For the maximum deflection, we have to assume we don't know the distance, okay? We don't know whereabouts the maximum deflection will occur, okay? So for that we assume a general distance x, okay? So what was our TC by A? Please, can you tell me? 400 by? That is no. Okay?
Sir,
400 over EI.
400 over VI. Okay, that is our TC by A. we need TC by A. Look, we have to work out our delta in terms of x. In other words, okay, delta in terms of x. That's it. So TC by A we know. Okay, from similarity of triangle. This time, instead of 1, we would have it at x meter. Agreed? This is x meter. B is somewhere x. So similarity of triangle BB prime is equal to agreed? BB prime would be 400 by 3 into x. dB by A is equal to 1 over EI x square over EI.
सर ये 3 कैसे आ गया?
और
सर ये 3
wait.
middle step in the denominator.
This one.
Yes.
This is a similarity of triangle I have done. Sorry?
The similarity of triangles.
TC by A, didn't we discuss? TC by A divided by 3 is equal to?
सर वो तो B के लिए था ना, अभी हम X के लिए कर रहे हैं ना, उसके लिए 3 था सर, अब तो X आएगा ना, उस केस में 1 में 3 था तो 3 आया था सर, अब X है तो
Guys, I think you guys need to revise your A levels. Okay, again. This is, look. This is our triangle. This is TC by A. This is X. This is 3. And this is now TB by A. And this is X. So, TC by A by 3 is equal to TB by A by X. So this 3 will exist. It's only this thing which will change. Got it? Yes?
Sir,
Any question?
Yeah, वो कैसे? How do we know that it is 100 like X?
Sorry? This is 100 Newton. So at X it would be 100 times 100 times. So this will be 100 into this will be 100 into x. Okay, so that means to say that this is 100 into x. Yes, and that means that this is this okay? Okay, now TV by A is known. Delta V is equal to TV by A, which is minus, sorry, BB bar. So BB bar is minus is this okay? Sorry? Now, what should you do? What should we do now? How can we proceed? The geometrically speaking, at the maximum point, at the point of maximum deflection, we have zero slope. Okay? So, in other words, must be equal to 0. Yes? So, x is equal to
So how did you write this equation?
sorry,
From where have you written this equation?
this equation. Now, I am saying that, guys, excuse me, the question came, how did we get this equation, sir? The one with the cap. How did we get this equation, sir? Yes, you. Sir, tell me whereabouts you don't understand. Tell me one thing which you don't understand. Which made you lose your interest. Just one thing. Sorry? So you are not interested in these questions, are you? Sorry? No, but you are not focused on this. Look, guys, please, we should maintain some discipline. Okay? So we have the question came, how did we get this equation? if I have got a curve,
So I know that the deflection would be zero at the method of
wait.
But I'm actually asking that how did you get this 400 divided by 3 EI minus?
This is delta B, and this delta B, we worked out BB prime, didn't we? And BB prime, what is delta B? Delta B is equal to BB prime minus the tangential deviation. So that's how we worked it out. It's similar to what we did previously. The only difference is that now we don't know where our maximum deflection is. Previously we knew, not the maximum deflection, but we were asked to find out deflection at a particular point. So we knew the distance. In this case we don't know. So I followed the same steps which we followed previously. Okay? Sorry? Okay, so what is x? Please give me the value. What is x? What is x? Come on, please give me. And there would be another value which would be negative. Yeah? That negative is of no concern to us. It is mathematically important. It is one of the root, but it is coming in the negative x region. So that is of no concern. We are only concerned with the positive. Okay? So 1.62 meter. Okay? Now plug it back in delta V. Okay? Any question? Is this okay?
Yes, sir.
Shall I rub it off?
Yes, sir.
Let me finish this. I'll give you 5 minutes. Okay? Shall I rub it off? Okay, so there is another way also. Excuse me. There is one another way of solving this problem. Okay, we went through the similarity of triangle and found our delta. But there is one another way also. How can we do that? Now imagine said that at the point of maximum deflection, our theta must be equal to 0. Do you agree with me? So, in other words, if I draw a tangent like this and another tangent like this, this is my distance x. Okay, I can find out my theta AB. Agree? Can I find out my theta AB? What is theta AB? 1 over EI area what? AB. So that is my theta AB. Okay? In terms of x, I can find it out. Agree? Now, would you agree with me that this angle would be equal to this angle? Do you agree with me? So if these two angles are equal, can't we find out theta A? Can we find out theta A? What is theta A? How can we find out theta A? TC by A by 3. Agreed? 400. So theta A is equal to 400 Is it okay? Is this 400 by 3 EI TC by A is?
10 inverse.
Look, we are doing small displacement. Okay? So tan theta is approximately equal to theta. So therefore we omit tan. And so 400, this TC by A was 400. Yeah? So this is 400 by 3 EI. Agreed?
सर बी बार और थीटा ए बराबर हो गया मतलब पिछले मेथड में बी बार फाइंड किया था हमने.
This is, and we are talking about theta. BB bar was deflection. This is theta.
लेकिन दोनों का आंसर तो सेम आ रहा है 400/3 EI.
How? This is okay. So this might be whatever it is, but these are two different entities. Okay, one is rotation and one is deflection. Okay, they are not different. So one is in radians and one is in the unit of length. Okay, so now what is 1 over EI area AB? What is that? What is area AB? Half into 100x into x, isn't it? Is that true? So can I say Can you find out x first? Sorry? One point. This is the same. Okay, that's the other way of solving maximum deflection. So the main thing to remember in this one is that your angle is horizontal, and if your angle is horizontal, at the maximum deflection, your tangent is horizontal. Okay, so tangent being horizontal means that you can have your two corresponding angles equal. So theta A is equal to theta AB. Okay, these two are equal. So this one is theta AB. This one is theta AB, and that one is theta A. Sorry? Theta AB is area covered between A and B. Sorry? Sorry?
So where have you drawn theta AB here as in this?
Theta AB. Where is theta AB?
Yes, sir.
So this is your theta AB. What is theta AB first of all? What is your theta AB? It is the rotation
Yes, sir.
between two tangents. Relative rotation between two tangents, one drawn at A and another one drawn at B. So this is the one at B and this is the one at A. So this angle is theta AB. Okay? Okay?
Yes, sir.
Yes. Sorry? Sorry, say it again. I couldn't hear you. Can you speak up, please? Which? This x. This x.
It is a distance.
This is a distance.
From A.
This is the distance from the support, and at this particular distance, we are assuming that we have maximum deflection.
What's the B point of the mark?
So B point, I'm saying that this is just one point. You can call it anything.
You don't know the distance between A and B.
Yes, why? Because we don't know where the maximum deflection is occurring. If this was in the middle, if this rope was in the middle, we could have said, using our intuition, that maximum deflection will occur at mid-span.
Sir, generally your deformations are
No. If your load is applied close to the support, then it's not deformation, it's the deflection. Okay, hold a string, apply load over here. What will happen? You can have, sorry?
I cannot visualize that.
I'm saying, if you have a string, it's not like a string. Okay, it's not like a string. Like for example, I've got a beam. Okay, I apply load over here very close to this point. Okay, so what will happen? I will get a deformed profile. So at that particular, imagine that load is very close to my right hand. Okay, very close. Still I would get a deformed profile. So that doesn't mean that you will have maximum deflection over here. Maximum deflection can be somewhere in the middle. Okay, unless and until your load is applied at mid-span, you can have maximum deflection. Is that okay, guys?
Yes.
Yes. So that is your moment area method. your first assignment, your assignment plus quiz. Okay, so that is a take-home quiz. Okay, so assignment plus take-home quiz is that you have to do the exercise questions, which have got those exercise questions which have got the answers. I'm wrapping it up. Okay. Can you stop recording? I'll give you 5 minutes break.
Thank you, sir.